All right, we are transitioning into our next unit, which is all about acids and bases. So I'm sure you've heard of these things, especially acids. I feel like they are used often in movies, right? Typically, maybe there's some kind of accident in some kind of lab and an acid is spilled and like all of a sudden there's a hole burning in something or someone's hand is burning, right? We see this kind of happening sometimes in movies or TV shows. If any of you might have watched Breaking Bad, um, there is a one infamous scene where they allegedly dissolve a body in acid. I'm not necessarily going on based on facts here, like that's not actually true, but this is how we can see them sometimes in kind of pop culture, but we're going to take a look at what they actually are chemically speaking, okay? So, back in the day, people kind of referred to these things that acted a certain way as acids and people that acted in a certain way as bases, but there wasn't a really good definition. And so back in the 1800s, a scientist named Arrhenius, he kind of came up with this working definition of what an acid is and what a base is. And so based off of this definition, it's an acid is anything that produces H plus in solution. Remember, solution means it's dissolved in water. So an acid is anything that produces H plus in water. Okay, so some examples would be like HCl, hydrochloric acid, right? That's what's in your stomach. H2SO4, this is sulfuric acid. HC2H3O2, this is acetic acid, aka vinegar. Okay, so if you dissolve these things in water, remember, I don't know if you remember this, but back earlier in the year, we talked about things that conducted electricity, and we took an acid and we put the little light bulb setup in it and the light bulb lit up. And why was that? It was because the acid split into ions, okay? When the acid split into ions, that allowed electrons to move through it, and so it lit up in water. Maybe you're remembering this ever so slightly, vaguely, okay? So these things produce an H plus and some kind of negative ion when they dissolve in water, okay? And then the base definition is anything that produces an OH minus ion. This is called hydroxide, okay? It's on your polyatomic ion sheet. Anything that produces a hydroxide ion in solution, remember, it's when it's dissolved in water. So this is sodium hydroxide, this is lithium hydroxide, this is calcium hydroxide, okay? So these are all things that when they're dissolved in water, this was split up into Na plus and OH minus, this would be Li plus and OH minus, and so on. This was a really good start to kind of have some scientific definitions and like kind of guidelines around this. But it wasn't a complete full definition. Okay, so before we get into that kind of more complete full definition, I want to talk about hydrogen for just a second. Up here, this is a picture of a hydrogen atom, right? It's element number 1. It's got 1 proton, 1 electron, no neutrons. Okay, a hydrogen ion, remember hydrogen is in group 1, so it forms +1. So what does that +1 mean? +1 means, imagine covering up this electron, right? If it gives that electron away, it's just going to have 1 proton, which gives it a +1, okay? So this is kind of showing this too. If it gives away its electron, all that's left is this proton, okay? So a hydrogen ion has 1 proton and no electrons, which means that a hydrogen ion is really just a proton hanging around, okay? Which leads us to our next definition, the Bronsted-Lowry definition. Again, made by a couple of scientists working together, one with the last name Bronsted, one last name Lowry. And so their definition said that all acids are proton donors, okay? Which means they give away a proton, and all bases are proton acceptors. One big difference between this definition and our last one was that they do not have to be dissolved in water, although oftentimes they are, but they don't have to be. And all the Arrhenius ones, all of these guys, okay, they all qualify as acids and bases under this definition. But the reverse isn't always true, okay? So what we're going to do now is we're going to take a look at some examples and kind of how this works. Okay, so going back, one of the things we wrote down under the Arrhenius definition was HCl, a hydrochloric acid. So let's take a look at this. If we were, this splits apart into H plus and Cl minus, okay? So we look back at our first definition. This produces an H plus in solution. Great, so definitely one of those. And based off of our second definition, is it a proton donor? Yep, it sure is, because this is a proton, okay? So HCl is an acid under both definitions. Let's look at base that we had written down, which was sodium hydroxide. Okay, when this splits apart, it goes into sodium and hydroxide. Based off of the Arrhenius definition, that OH minus is the hydroxide ion. Okay, so there it is. Based off of the Bronsted-Lowry one, it says it's a proton acceptor. Well, is this a proton acceptor? It turns out it is, but it's not as clear. So since this is an OH minus, we could take an OH minus and we could add a hydrogen to that. And do you know what happens when you take H plus and OH minus? How many H's do you have? 2. How many O's do you have? 1. The plus and minus cancel out. Oh, you make water. Cool. So it's not readily visible that this is a base based off of the Bronsted-Lowry definition, but as it turns out, because this thing has the possibility of accepting a proton, that makes it a base. So it is a base under both definitions. It's really easy to see under the first definition because there's that hydroxide ion, but the other definition takes a little bit more thought. Okay, let's look at another example. So, I mean, obviously acids should be pretty easy to see because they're a proton donor, so which means they're going to have a hydrogen in them, right? So no matter which definition you're using, acids are really, really easy to figure out. Bases oftentimes have an OH minus, okay, have an OH in there, but not always. So let's take a look at a base that doesn't necessarily have an OH minus in there. Okay, this is going to be something like NH3. Okay, this is also known as ammonia. And if we were to draw the Lewis structure, it looks like this. Okay, if we were to draw out what that looks like, this has a trigonal pyramidal shape. Okay, just a little review there. Okay, so when NH3, when we put it into water, as it turns out, although it has hydrogen, it doesn't release any of these. Not at all. It holds onto their hydrogen. Okay, so not an acid there. But how do we know it's a base? It doesn't have an OH minus here, so it's not a base by our first definition. But what about our second definition? And like I said, it's a little bit harder to figure the bases out. But as it turns out, notice this lone pair of electrons. Guess what can go there? A hydrogen. A proton. And so if that proton moves in and goes there, then you're going to have NH4. Okay, it's going to have a charge of +1. This is the ammonium ion. Okay, this would have a tetrahedral shape. And so as it turns out, because it's got this lone pair right here, it can accept a proton. And so it is a base under our Bronsted-Lowry definition. Again, the bases are a little bit harder to figure out if they don't have an OH minus in them, right? And this is really the main one that you'll see is that ammonia is a base. And the acids, again, typically easy because they oftentimes start with an H. They're an H plus donor, but don't get confused by this one. There's an H there, but it's not an acid. Okay, so usually acids are going to start with H, right? They're going to be a proton donor and donate that H plus. Bases oftentimes have OH, but not always. And they're going to be a proton acceptor. So hopefully you jotted down some notes about what makes an acid and base in our kind of two different definitions. And hopefully you jotted down a couple of examples as well.